working on, and one of them is turbulence in relativistic MHD. So this is driven in this particular model by a shear layer, so it's Kelvin-Helmholtz that goes nonlinear. And what we find is that for conditions for internal shocks and gamma ray bursts and late afterglow phases, that the magnetic field energy density saturates at 0.5% of the total energy. So this is what we think is a good way to produce magnetic field in GRB outflows. And the idea of what drives the turbulence could be anything, but Amir's talk yesterday was quite interesting. That's something that could drive turbulence for a long time. This could also be driven just by inhomogeneities in the outflow. But the idea is that when turbulence saturates, we get converged magnetic fields, and this is 1024 cubed, relativistic MHD. And what we find is that there's islands in the turbulence that are in equipartition, so the field can't wind up anymore. And so at that stage, we can just add up the total magnetic energy in the box compared to the total energy, and we get 5 times 10 to the minus 3. This is usually a free parameter in afterglow modeling. So we think this is a good value to use.
Total energy is basically the turbulence energy?
Yeah, it's about the turbulence energy, exactly. So, yeah.
How sensitive this result is to initial conditions?
They could be quite sensitive, and so my only claim is that for the conditions we've used, which are, like I said, internal shock, so mildly relativistic P over rho. So the internal thermal Lorentz factor is about 2. So for those conditions, this is what we get. So we have to try other conditions, of course. And also, what we've done is, and I'll show you a little bit later, and you saw the movie last time, this is a shearing layer where the middle of the box is going one direction and the top and the bottom quarters are going the other direction. So it could depend on boundary conditions and so on. But this has to be checked. But I think the saturation mostly has to do with turbulence.
But in the typical internal shocks, you don't have shear motions, you just collide.
Yeah, well, that's the thing that so I'll argue that you might, and Amir also I think his arguments would also apply for internal shocks. So yeah. Okay, then the second thing, which I also showed last time, but I'll give you a few more details, is adaptive mesh refinement. So so actually.
Don't assume you know anything.
Sorry, okay, I don't assume anything. Okay, what's going on here is, this is just to show you the grid. So it's a spherical numerical grid that's changing adaptively in time in order to resolve extremely thin structures. So this just gives you an idea that when it's washed out in blue, that's 16 levels of adaptive mesh refinement. So what the code has done is it's found a sharp feature up here, which is a relativistic shock, which has created a very thin shell of material that's moving relativistically. And because it's detected that jump in density, it's created iteratively finer and finer resolution to resolve the very thin shell. Because I think, so in the Blandford-McKee solution, which describes a spherical relativistic shock, the energy and density in the shell in the lab frame is compressed into a very thin shell of width r over gamma squared. So it's a very thin structure, so it's hard to resolve. So what this code is doing is it's automatically refining until we resolve that shell. And I'll show you a little bit later, we don't solve it exactly at early times. So this is an explosion at late times. It started with a Blandford-McKee patch down here, which is this high resolution regen. And then what we did in 2D, so it's an axisymmetric simulation, was we allowed the Blandford-McKee to expand. And then at some point it slows down enough, because it's sweeping up more and more mass, it slows down enough that the Lorentz factor is less than the 1 over the opening angle, which was 0.2 in this case, and it starts to spread sideways, and then we get this structure. And what I'm going to show you is light curves that we've calculated directly from the two-dimensional simulation. Yeah?
I have a technical question about, I mean, when you change your grid size, you might run into numerical stability problems. So how do you take control of this?
I'll show you.
Oh.
Yeah. Okay, so anyway, that's an overview. And in these calculations that where we calculate the light curve, basically we know the energy density everywhere in this fluid at all times. We save 5,000 different time slices of this data. And then we can put an observer either on axis or off axis, and just set for a fixed observer time, sum up all of the radiation that's emitted, just assuming standard synchrotron models for emission. Nothing's changed there. The idea here is to replace what are simplistic analytic models with a numerical calculation of the dynamics. And so from that we get light curves, which I'll show you. I flashed them last week as well. Okay, so I called the talk jets originally. I just want to draw a distinction. This is an AMR simulation of a jet in a star. And the point is that the jet stays relativistic because there's a strong shock that it drives into the star, and that material is allowed to go sideways because this material is not moving relativistically. The blue stuff is. But what you do is you build a cocoon of hot material that surrounds an ultra-relativistic core of a jet, which is capable of escaping the star. So what I'm going to talk about now isn't this jet. So imagine you have the jet in the star, but that's going to drive a ejecta that's going to sweep up the ambient medium, and at some radius it's going to have shared all of its energy and momentum with the ISM, or the circumburst medium, which could be a wind. And that's the shock that I'm going to talk about. So we start with after this ejecta has swept up enough material to launch a shock into the ISM. So its energy has been gone into this material, and this material is now traveling relativistically. So it's a later phase. So what Amir was talking about yesterday was this phase in the early afterglow where there's still a reverse shock going into the ejecta. Where I'm going to talk about now is after this shock has been fully launched and this material has been decelerated. Okay, so the shock is in the ISM. Okay, and then the initial conditions are Lorentz factors of hundreds that we know from compactness arguments from the prompt emission. But we're going to pick it up on Lorentz factor 20. So we're going to assume that the ejecta has launched a shock, which is Blanford-McKee, in a patch of opening angle 0.2. So this is our initial condition. We have a thin shock. Its opening angle is 0.2 radians. And its initial shock Lorentz factor is 20. And the energy in the explosion, E iso, is 10 to the 53 ergs. But the total energy, is the real energy, because you have to correct for the opening angle squared, is 2 times 10 to the 51. So that's the true energy, and this is what the energy it would have if it were a full spherical patch. Okay, so is that clear? I'll show it a little more clearly in a second. I wanted to show that this is an impulsive, this is what happens if you just have ejecta that comes out as a jet. What can happen in reality is the engine can keep on going for a long time, and this is something we showed a long time ago, just from fallback in the star. So if you have a jet that drives a shock through the star, there's still material that can fall back in the equator and keep the engine going for days. So in that case, we'd have a different solution, which we're not doing right now. Yeah?
You are assuming that Blanford-McKee solution is valid up until region where Lorentz factor goes down to 20.
Yep.
But then you show in your initial slide that at a certain point the jet spins sideways. Cannot this happen already before the...
Absolutely, and that's exactly what I was showing here, is this phase where you set up the shock. It's not even clear. Blanford-McKee is set up when you have a spherical shock wave, because you conserve all the energy inside of a sphere of radius r. But in reality, you're absolutely right. What's actually going to happen is as a blob pushes its way into the ISM, it's going to shock this material, it's overpressured, and it's going to go sideways, just like I showed in that jet simulation inside the star. So it's not at all clear that you'll have Blanford-McKee at all angles. In reality, you'll have a more complicated structure where it's maybe close to Blanford-McKee along the axis, but there's some other gamma and energy density as a function of theta, where theta is the angle with respect to the
So how can you justify this assumption?
So we're justifying this assumption by taking one step away. So essentially what we're trying to do is do, in a hydrodynamical model, the evolution, assuming the initial conditions that are assumed by all of the analysis that's been done so far. So we're just trying to change one thing, which is to follow the dynamics. So, but in reality, yeah, this is also an interesting question, but one step at a time. Yeah.
But in general, any rarefaction would travel mildly relativistical inside this. So this gamma 1 over theta argument.
Yeah, I mean, that's exactly what I'm going to show, and as you know, because it's much more complicated, and what you actually see is a rarefaction going at the local sound speed. towards the axis, and it's a much, and I'll show exactly that. Okay, so, but I just wanted to make the point here that the engine can keep on going, and then you get something else. You have a powered shock, but we're not considering that case. This is an impulsive initial condition. Okay, and then I showed this. I have this great thing that you had, Amir, last time as well, but it's not supposed to. It's supposed to be constant density medium. And I just wanted to emphasize that indeed the Blanford-McKee solution is a spherical solution. And the point of showing this is just to show the need, and I showed this last time, the need for high resolution. The need for that is because the structure that you get is that the shocked, all of the energy in the shocked ISM, or circumverse medium, is concentrated in a very thin shell. So that's difficult, that's a numerical problem. And that's why we use this adaptive mesh refinement technique. And I showed this as well, that these blue lines just represent patches of 8 zones. So where we need them, we put the code automatically includes that resolution, and that changes as a function of time. So it's constantly creating new numerical grids where they're needed and removing them where they're not needed, so that you resolve as best as you can this thin shell. And I'll show you that even as hard as we tried, we didn't exactly resolve the shell at the very earliest phase.
Is this done as a 1D or 2D?
This is done in 2D. I'm just showing it in 1D because it's easier to show. But basically, you can imagine that first picture, which would be much more complicated, but it's doing the same basic thing for 2 or 3D. Just adds it adds the grids where they're needed. Okay, and then the other thing that we're interested in is that initially Blanford-McKee goes like T to the minus 3 halves, but we're interested in the phase where the explosion transitions to the set-off phase. So we want to see, we initially have a relativistic explosion, but in order for an explosion to be relativistic, its energy has to be greater than the rest mass energy that it swept up. At some point, the shock becomes so large, it swept up so much material, that it transitions to a non-relativistic solution. That's called the set-off solution. That would be the same as what you'd get if you just exploded a supernova, a normal supernova. But so these are both similar solutions that are easily derivable, or straightforwardly derivable. And then the interesting thing that has to be solved numerically, which is what we do, is this transition also as the blast wave decelerates and becomes non-relativistic. So this part has no analytic solution and has to be solved numerically, even in 1D. That's a relatively simple hydrodynamics problem.
So
But yeah,
this is all adiabatic?
this is all adiabatic. Yeah, so everything here is yeah, exactly.
So what happens, I mean, well, obviously gamma ray bursts can't be adiabatic.
They're not completely adiabatic. So what we're assuming here is the energy that's released is a relatively small fraction of the total energy that's in the explosion. So as soon as the cooling rate becomes greater than the energy in the explosion, over some time scale, then this assumption breaks down. So we haven't considered that, but we can, because in principle we can, because we know what our synchrotron emissivity is, and we could remove that energy from the blast wave. That could be important in some phases. We haven't done that yet. That's a more complicated model, but certainly doable. But we want to keep things as simple as possible. Yeah, it's like in a supernova. The adiabatic it's roughly adiabatic.
That's right,
Yeah.
that time.
Okay. So then there's this interesting time when the Lorentz factor has, and it's not a very simple thing, but just very roughly you kind of expect order of magnitude when the thing is slowed down enough. In the analytic models, they just said, okay, when it gets to the radius where the Lorentz factor is 1 over theta jet, then it just expands at the speed of light, or the speed of light times some factor less than 1. But what we're doing is actually calculating what happens, and that's what I'm going to show you. Okay, and then at light times it becomes Newtonian. But all of these phases are in the 2-dimensional simulation, from relativistic to the spreading phase to this Newtonian phase where it becomes a spherical set-off blast wave.
Wait, these are MHD or just?
These are pure hydro.
You don't need
Relativistic hydro. There's no MHD. So the assumption is that there's some, this is again, the standard model is that you have a parameter, epsilon v, which tells you the fraction of magnetic field as a function of the total energy density. And I also showed this last time, but I wanted to point out that, because it's important to know, it's always good to be clear about what the technical difficulties are. So I'm not going to pretend that this is an easy problem to do. And it's a very simple thing, a Riemann problem, which is two constant states which drive some dynamics. But a Riemann problem, when you have a transverse component of velocity, is difficult to solve in the relativistic case for purely technical reasons, which I'll show. So under-resolved Riemann problems solved numerically have the wrong speeds. And so that's bad. Normally in numerics, if you're under-resolved, you just wash out some feature. So it just becomes more diffuse. You might expect a shock, but you get something that looks more like a ramp, for example. That's not the case here. This is a worse problem. If it's under-resolved, the speed is wrong. Right? Bad problem.
If you have adaptive mesh, you can solve it, right?
Sorry about that.
Yeah.
But
But adaptive, well oh, whoops. What have we done?
it's getting worse and worse. But
I'm going to move this.
Adaptive mesh will not.
I'm gonna show you in a second. But yeah, so we've only solved it by brute force. I think, in principle, there might be a way of rewriting the brute force is using AMR. So there's a
What is
feature
AMR?
there.
Adaptive mesh refinement.
Adaptive mesh refinement. Sorry, yes. Adaptive mesh refinement is what we call this technique where you detect features that need resolution and adaptively refine them. So it's a complicated algorithm, but in principle it's very simple. But that's what's required. So but the point is, this Riemann problem where you have a shock in one direction and there's transverse components of velocity seems really simple. In the Newtonian case, you just vect transverse momentum with the flow. It's not coupled. But the point is, in the relativistic case, the Lorentz factor depends on all components of velocity, so that if you under-resolve features of the flow, it turns out to be numerically difficult. Okay, and this is the reason. So it's just this coupling. So this is just these are the equations of special relativistic hydro. They're straightforward, and in principle, they have all of this dynamics with lateral, and everything's coupled through the Lorentz factor. But it's because of this coupling, where this v depends on all components of velocity, that we have this difficulty. And I'm not sure it's fully understood, but it can be solved just by brute force.
Equation of state there.
So this equation of state is just a gamma law. So it's an adiabatic equation of state. And we use a interpolation between a relativistic and non-relativistic gammas, because we're trying to do both the relativistic case and the non-relativistic case.
What's epsilon here?
Epsilon is the internal energy density per gram, the specific energy. Rho is the mass per unit volume. And so gamma in this case, that's why we're using W for the Lorentz factor. Gamma is the adiabatic, it's the ratio of specific heats. Okay, and then the point is that when we're talking about relativistic hydrodynamics, it could either be that the Lorentz factor is larger than 1 or much larger than 1, or it could just be that the temperature is high enough. So P over rho, where rho is the mass density. Think of it as rho c squared. We're using units in which the speed of light is 1. So if the energy density, the thermal energy density is large compared to the rest mass energy density, then you're also relativistic. So even if the speeds are slow.
You said adiabatic law, but it's perfect gas.
Perfect gas, that's right.
So can you, I mean, how do you take care of stability when you change your grid size?
Oh,
Because
yeah.
you have convective terms, say, with non-uniform. If your coefficient, say, are constant, it's not a problem. But if they depend on time and position, I mean,
Yeah, no, you're right. It does make the things more complicated. It'd be much better to do
There is
it.
an algorithm.
Yeah, there's an algorithm to do it, but what it does is it conserves fluxes of energy and momentum and mass between different levels of refinement. But you're right, different parts of the solution have different.
Surfaces, I mean.
Sorry?
Near a surface, it's might be a problem.
Yeah, I mean, usually the surface of the shock is always at the same level of refinement as it moves, because that's the maximum level of refinement. But you're right in principle. Technically, it's a little bit iffy to have variable resolution in space. We have to do it because we can't afford It's just we have to, because we can't afford to resolve the entire domain. We're talking about a really thin shell that's moving very far in radius. So we can't afford to put that level of resolution everywhere that we want. So that's the problem. So we have to check these things, and we check them as a function of resolution to make sure that things converge. But that's the best we can do. Okay. All right. So and then these are these Riemann problems, and what you have is this is a space-time diagram. So if you have some sort of discontinuity in the fluid, and let's say the pressure is higher on the left than on the right, what you get is that there's a shock that's driven to the right. It's just the pressure gradient pushing, and there's a shock wave that goes to the right. And then the initial discontinuity between the high pressure and low pressure fluid is called the contact discontinuity. And that moves also to the right at a slower speed. But then what the high pressure region, there's what's called a rarefaction fan. So if you had high pressure here, low pressure here, then there's a wave that travels into this high pressure region, communicating the fact that this barrier is gone and that the fluid's moving to the left, or my left. Okay, so this is the so-called rarefaction fan, and this is the thing that can be tricky in the relativistic case. So there's the head and the tail of this rarefaction fan. Okay. Okay, and then again, this is just a one-dimensional problem. And then the problem is if there's a y direction, even in a 1D problem, if there's a y velocity, a transverse component of velocity, that should just be affecting with the flow. That's the thing that can cause some problems. Okay, and then there's typical tests that people always do. It's called shock tubes, where you just test your code because you know exactly the solution that you should have, which are the solid lines. And what you do is you sum up the difference between your computed solution and the exact solution, and then you get some sort of norm of your error, sometimes called L1 is a very popular norm to take. And as a function of resolution, you increase resolution and that error should decrease in principle. So, and it does. But the rate at which it decreases, the error decreases as a function of increased resolution, gives you some measure of the accuracy of your code, so the convergence rate. Now, these problems where you have strong discontinuities, all codes are diffusive because they have to, so they're at best kind of first order accurate. But in regions, but what we have in this problem is we have both a strong shock, and then we have this dynamics behind it where there's some flow going on, which can be relatively smooth in some regions. So it's also good to have a high order of accuracy in the smooth regions. This is just a different test showing extreme compression in the relativistic case. You can get compressions that kind of go like the Lorentz factor, so the energy, the specific energy, which is roughly the Lorentz factor. So in this case, the Lorentz factor was something like 70,000. So you can get compressions of hundreds of thousands or something. And this just shows that these codes have a little bit of trouble with it, but they do it pretty well. So this is the shock and at fairly low resolution. So we can handle very relativistic flow. And then in 2D, this is to show, someone asked about the AMR in 2D. So this is just a typical, a very standard test case where you have a wind coming from the left and it encounters a step. It's called the Emery step. It's a test problem. And I'm just showing this to you to show you how the AMR, what it does, is as this thing comes in, it's resolving all these structures. There's a standoff shock here, and all these structures are resolved by this AMR. Okay, and that's happening in time. Okay, so here's a test of some problems with AMR. So this is called the no. It's the no problem. It's a spherical implosion where we know the solution exactly. That's the solid line. And what we're showing here is this is a radial. It's in spherical coordinates, so it's a radial implosion. We're showing the transverse velocity, which should be 0. And what you can see here is these are small numbers. So this is 10 to the minus 12 is this red. But you can see in this flow that's just coming in, there is some noise introduced by this adaptive mesh refinement, but it's very close to numerical round-off error. So, machine precision. It's very close to that. So there is some error introduced by AMR, but it's very small.
What exactly did you do here? You started with...
So you just start, it's like throwing gas at a wall. So you have a reflecting boundary condition, and you just start the gas off relativistically moving towards it, and it drives a strong shock, which you see here. And so this is the post-shock.
But
Yeah.
it's spherical and
Spherical, and it's moving inwards
and your initial
radially.
condition is, I guess, the transverse velocity is zero in your initial condition, and
The-
you're looking to see if it drifts. Or,
Right. All the fluid is cold and fast, and it's moving inward.
yeah.
So it compresses, and there's a shock, and at which point it should be exactly at zero speed.
Right.
What I'm showing you is that there's a little bit of noise in the lateral direction, but that it's extremely small. That's the point of this. And also that the AMR, introduces a little bit of extra noise. So this is 10 to the minus 15, and the fact that the grid has been refined introduces a little bit of extra noise, but it's still on this very small scale. So there's not a lot of error that's introduced by the AMR.
So you run it for long enough time to see that.
Yeah, we run this for a long time, and we check how, as the shock moves out, that we get this density jump right, and we can check this L1 thing as a function of convergence with AMR. And so we do our best. Okay, so anyway, right. And then, so this is what the method that we use. It's called WINO. And we use, it's fifth order in space and fifth order in time. And what we've demonstrated is in smooth regions of the flow, where we know the exact solution for some smooth pulse that's supposed to be moving around, we can compare in 1D and 2D, so multi-D, we can check how the error decreases as a function of increased resolution. And we find the convergence rate is really fifth order. So we do this, we have many tables of different test cases. It's kind of technical, but it's important because you want to get the best resolution you can for a given amount, best accuracy you can for a given resolution. So this method has been demonstrated to be fifth order. And then this is the problem that I mentioned before, that 400 zones for these test problems is a lot of resolution. Usually people show these tests at 100 zones. And then for 100 zones, it's so terrible, it's kind of embarrassing. But at 400 zones across this Riemann problem, you can see that it's not just that the solution is under-resolved. So what we have is high pressure, low pressure, but we have a y component of velocity of 0.9 c on both sides. So it's just, there's a boundary here, there's high pressure, low pressure, and then there's a velocity component of 0.9 c on both sides. And so what this is going to do is it's going to drive the shock, so you're going to start to get gas flowing in this direction if P1 is greater than P2. But just the presence of this velocity shear messes up that shock. So it travels at the wrong speed. And it's because of poorly resolving this feature.
Why is that?
Yeah, so it's hard to, I think it's because the momentum and energy depend on different powers of the Lorentz factor, and you're doing these interpolations.
This is a pure
But
numerical thing, but if both
it's purely
the
numerical.
y the same, and you can just move to this frame.
Yeah. So what's the problem with that? You think you could just boost laterally, solve the Riemann problem without a velocity, and then boost back?
I'm just asking, yeah.
No. So what's wrong with
that's
that?
not.
Why not?
Because once you get, you start getting motion in the trans direction, and then what he's saying, your Lorentz factor depends on the sum of the radial velocity and the
Right.
tangential velocity. So you have a mix. It's a
Yeah.
very difficult problem.
It is a difficult problem, but that's not the reason you.
I'm not saying it's so difficult, just want to understand exactly.
So what's the problem with boosting? Anyone else laterally? This is just a one-dimensional problem, and there's some interface. So why can't we just boost laterally? So, okay. The reason is it's simultaneity. It's no longer, if you boost laterally, this is no longer a one-dimensional problem. You'd have the constant time surface would be at an angle. So it's a different problem.
For steady state, we'll get alright.
For steady state. Yeah, so you could try it actually.
Not steady state.
Yeah. But, so you can't do that. And so you have to solve it with these transverse velocity components. And the solution is known. It's not a problem. This is a well-known thing. These solid lines are the exact solution. It's purely a numerical artifact. And it has to do with this noise at this interface. And by the way, it's not method. So we've tried all methods. We tried PPM, WINO, all these different things. All the standard methods that are used for relativistic hydro. and they all have this, for multidimensional relativistic hydra, and they all have this problem. So it's not a particular scheme that's wrong. There is one called GLIM, which works in 1D, which can solve this, but that doesn't work well in 2D. So anyway, the brute force method is just to use AMR. So we just allow the grid to refine where it needs to, and we do converge to close enough to the right solution. And so we make sure we're using at least this level of AMR, or this level of resolution if necessary, to everywhere, to resolve this this problem.
But
And
this
at
level-
a very high resolution, you converge almost exactly, but there's a little bit of an overshoot here. Yeah.
But this level of resolution will be dependent on the velocities, right? If you increase the velocity, then you need higher level, and vice versa. So, and what can you learn from this exercise and solving?
What you learn from this exercise is that you look at you know what the conditions are. It's not an arbitrary thing. So if you're solving a certain problem, you know what Lorentz vectors are, and roughly what your conditions are, what the pressure is, and so on. And then you use the level of refinement that you require. That's what you learn.
Yeah, but I mean, 0.9 C is mildly relativistic.
It's mildly relativistic, yeah.
And when we speak about, gammas of 20 or so, it's much higher than that.
Yeah, but we're talking about the speed of stuff going sideways. So 0.9 C is about right. It's a Lorentz vector. Okay. Anyway, so that's just a technical thing, but it's good. It's just important to be honest about that. And then I showed this last time also that because we're solving, so this blast wave is initially relativistic, so the gas behind it is relativistically hot, so we should use a gamma of 4/3. But downstream from that, so the gas is decelerated and it cools down. But downstream, it's no longer relativistically hot, and there's some important dynamics that we want to solve for. And also, as the shock slows down enough and transitions to the set-off phase, the post-shock temperatures are low enough that it's a ideal non-relativistic gas, and we want to use gamma 5/3. So this turns out to be a very simple way to do it. That's inexpensive. So the solution, the correct equation of state is known, but it's numerically expensive. But you can use this form instead, and it's good to within a few percent everywhere. And in particular, what you can see is in this particular shock, there was high pressure on the left side, and it drove a shock that was so strong that in the shocked gas, you start to get gammas that are 4/3. So down here, this is the shocked gas. And then upstream, the gas that isn't shocked yet, is 5/3. So basically, in this red line is the exact solution. So this thing works. And then this shows the difference between the dynamics you'd get if you just use 4/3 everywhere, which you don't want to use because you're assuming in these explosions that the ambient medium is cold, and you're driving a relativistic shock into it. So the pre-shock gas should be 5/3, and the post-shock should be 4/3 initially, and then at late times everything is 5/3. So it becomes cooler. So so what do we do? So what we do is we start. This is a radius versus angle. So this is a patch of the Blandford-McKay solution like this, and the radius goes like this, and then our opening angle. We actually do this axisymmetric, so is 0.2 radians. Okay. And so what we do is we try to resolve this initial condition as best we can. So we use several thousand zones in this direction, and then in this energy-containing shell, we use 17 numerical zones. That's the highest resolution we've been able to do. And as you'll see, that works pretty well, but it's not exact. It's not really high enough, so we have to try even higher resolution.
The axes are too small to read.
Yeah, sorry. So this is radius, and this is angle. So this is r, and this is theta. So this is a polar plot, and it's showing this. It's showing where the energy is in the Blandford-McKay solution as the energy has been transferred into the spherical shell. So this is a little patch of the spherical shell, and this is the ambient medium. Oh wait, down here. So it's theta and r. And then what we use is 16 levels of adaptive mesh refinement, and we have so the equivalent of a lot of zones. But if you looked at this with AMR, you just see high resolution in the shell and along this edge, and everything else would be a relatively low resolution. But then as the shock moves to the right, that resolution would follow it. Okay, and so the initial length vector in this case was actually 23. The ISO is 10 to the 53, and density was 1 proton per cc. Okay. So exactly, so that's just the initial condition. It's a patch of this spherical Blanford-McKee solution for a relativistic shock. Okay, and so here it is plotted in Cartesian coordinates. So here, this is the resolution of the screen. In reality, it's a much higher resolution here. And so we start with this angular patch of Blanford-McKee. The head of this shock is moving at Lorentz factor of 23. And then there's some structure behind it, which is described by Blanford-McKee solution. And then here are a bunch of different interesting times. And in particular, what happens is that the thing, like we said, it doesn't really stay. Even before this is before this jet spreading time. I should have written those times, but it already starts to spread sideways a little bit. So it's not like it stays completely beamed. And the reason for that is that the material behind the shock has a lower Lorentz factor, so it can move sideways earlier. So we get a slightly different dynamics, and it's a little bit hard to see, but what we see is there's a rarefaction that's moving inwards, and there's also a reverse shock from the material that's slammed into the ambient medium around it. And so, so we get this structure that looks a little bit like an egg connected to the jet, and this expands sideways, but much slower than you'd expect if you assumed that when you got to this T-jet time, that it would just expand as a top hat laterally. And I'll show plots that'll make it easier to see this. But this is just a map to show you what the density does as a function of time.
The expansion in the R direction is what you'd expect from the Blanford-McKee solution?
It is right here along the axis, but not here at the edges. So yeah, so the axis doesn't know about the lateral direction yet, because the rarefaction hasn't traveled inwards. So it's still just a relativistic Blanford-McKee solution along the axis. But at the speed of sound in the local frame, things are moving inwards, and then eventually this center discovers that there's an edge. So that's a hydrodynamic effect. What people have assumed previously is that the whole thing expanded as a top hat. And I'll show you that plot in a second. But yeah, so it's a little bit more complex, but it makes sense. I mean, you have to communicate this expansion inwards before the whole thing knows to slow down.
But that's roughly the sound speed in the frame of the contact, no? Something like that.
It's the sound speed, in the co-moving frame. If you're just moving along in this post-shock flow, the sound speed in that direction. So the contact, there's no contact anymore. In the Blanford-McKee, there's just a shock. The shock, yeah, just behind the shock, in the shocked fluid. That's right. And that'll give you the speed. That tells you how long it takes. But here's the thing, and I'll show this in a second. Maybe there's a better way to show it. But it takes longer for this thing to spread. And then this is a time scale when people thought it was a spherical, non-relativistic blast wave at 970 days in the lab frame. You can still see it's very jetted. So because of this effect that it takes a while for the edge to be known by the inner part, so this thing's still plowing along at its initial Blanford-McKee speed. So it takes longer for this thing to be decelerated and become spherical. So it actually takes 150 years before it, when people thought would happen at 3 years. So it takes 50 times longer for it to become isotropized. You know, I have some better plots where you can see this. Again, this is showing the density, and this is showing the energy. So because it's the same thing, just showing energy instead. But the point is that since we know the density and the energy everywhere at all times, we can sum up the synchrotron emissivity for a fixed observer time and plot light curves based on the emission from this jet. And in particular, for on axis, if you're off axis, the light travel time to the observer is longer. So you're at a fixed observer time, you're seeing the blast wave at an earlier time when it was higher energy. So it's kind of limb-brightened. So all of that's taken into account in these light curve calculations. Okay, and then you can see some of this dynamics here. And then there's also some complexity here. There's actually a reverse shock propagating into this rarefaction fan at that point.
And then the second plot, what is there? An oblique shock somewhere?
So there's the shock moving out, and then because it collides with the ISM, it drives a reverse shock. So that's the beginning of a reverse shock that's traveling behind the rarefaction. So the rarefaction is moving in, and then this gas moves out. It slams into the ISM, which slows it down, and that drives a shock that follows the rarefaction. I think I can show you a plot. It's easier to see if you see a plot of the thing. And this is the movie, and you can see it's a little complicated, and that there's Kelvin-Helmholtz, so there could be some mixing, which may be relevant for magnetic field generation. And this is going to go crazy in a second, but this just shows essentially what happens, and then it takes, so eventually we get this set-off solution.
It's too fast again.
Yeah, sorry, I don't have, let me see if I can control this. I'm not sure I can.
It looks like there is a very fast backflow.
Yeah, there is. There's not a lot of energy there, but yeah, there is. There's let's try this.
So the shock is already non-relativistic at this point.
At this point, it's non-relativistic, yeah. But earlier was, let me see. I guess I can just drag this. Yeah, okay. Yeah, that works. Okay, so let's do this. So here we start, where the head up there is relativistic. And then, so you can see that rarefaction traveling in from the side. It's a little bit hard to see, but it's that blue. And then it travels in, and then you see this extra feature. So this is the rarefaction traveling in, this blue feature. And then here's this shock that's driven by the material that's hitting the side. The material passes through the shock, and then there's shear here. So you get this Kelvin-Helmholtz instability on the edge. So you have rarefaction, shock, shock.
I'm confused.
Is that clear?
Yeah, but I mean,
But most of the energy is still up here. So at this stage, most of what you see comes from right here.
but that's
I'm not surprised by the fact that the filming point moves downwards quite fast, faster than the shock moves forward.
This thing?
No, well, at the very edge between the interstellar medium and the jet, well, there's a
Yeah.
shock, yeah.
Okay, but I
Well,
think...
there is an angle, and well, this point moves downwards very
No.
fast.
Yeah, you're right. I think that's because the material was already moving sideways earlier. It's hard to see. But the material that was, let's say, at an earlier time, the stuff that's up, that was already moving sideways because... so the initial Lorentz factor of 20 was here. Here, the Lorentz factor is only 5 or something. So it's a combination of this thing plus the fact that this stuff has kind of a head start. I think that's why it's so fast. See what I'm saying? Okay, sorry. So here's the initial condition. So if we looked as a function of radius, the Lorentz factor is doing something like this. So while it's true, this material is constrained to move.
And the shock Lorentz factor at this point, how high is it?
It's probably around 10. But we don't know.
Around 10.
Yeah. And so, but what I'm saying is that the material here is at a much lower Lorentz factor, so it's already starting to move a little bit. So there's this feature, which is the sum of the kind of pre-expansion.
so again the initial condition. I mean,
The initial condition is just the Blanford-McKee solution.
yeah, but how far it goes? I mean,
It goes all the way to the center. So the Blanford-McKee solution,
it's formally-
I guess, formally cuts off at some point, but it doesn't really matter because there's no energy there. So the very center maybe you should ignore. Because what we really care about is the energy containing part, and that's all, mostly right here. So, yeah, so the solution formally goes all the way. That's what we use.
Strictly speaking, is applicable for high gammas because it's a relativistic.
Strictly
so
speaking,
anyway, it's
but-
not applicable.
But as you might be aware, oddly, it works surprisingly well, all the way to Lorentz factors even below 2. It's amazing.
Yeah.
But it's derived throwing out factors like 1 over gamma squared, so it's amazing that it works as well as it does. Okay, so this thing, so then we get these kind of crossing of, it's a little bit hard to see, but you get these,
All the scales itself change.
The scale is changing, yeah. Yeah. Oh, we have to zoom out. Yeah. Oh, sorry, I should have said that. Maybe that's part of it.
Yes, exactly.
Yeah, we have to. The thing is expanding really quickly, so the movie is zooming out. So yeah, right. So you have to watch this. And this is also the reason we need AMR. So here it's close to the set-off phase, and now it's starting to just become non-relativistic.
So now there's only one shockwave, or
There's basically one strong shock wave. There's some vorticity here, which may be driving very weak shocks, but the main shock is just this thing, and then there's this Mach stem at the equator. Okay. So how many? Okay.
20 minutes.
All right. So now I'm going to show what this looks like along the axis and at the edge of the jet. And what you see is this is the Blanford-McKee solution, and this is the set-off solution, and this is at the equator. And what we see is that it initially stays on Blanford-McKee, then it slows down, and then it's converging to set-off at late times. But here's the problem at early times, and you'll see this in the light curve. I'll point it out. At very early times, we start with a Lorentz factor of 20, but we're not exactly resolving this peak. We have some sort of grid so we have some sort of average Lorentz factor which is lower. So the Lorentz factor immediately drops.
Average over what?
Average. So we're trying to resolve this very thin structure numerically. So we have some grid like this. So you never get this peak. So whenever you have a sharp function like this, you don't get the exact peak value. So you get a slightly lower value. But so that's the reason for this. So even at the highest resolution we can go, the average Lorentz factor that's numerically resolved is lower. But nicely, it joins the Blanford-McKee solution again at a Lorentz factor of around 8. So here we're fine. And this will have an effect on the early light curve. So at a day or something, where because Lorentz factor is too low, I'll show that in a second. It's easier to see. And then at late times, we converge onto the set-off solution at all angles. And this is showing the energy density also, which is, at very early times, is a little bit low by a factor of a few. So Lorentz factor is low by a factor of 2 or something like that. Okay, but then it does get Blanford-McKee here for this phase, and then it makes this transition. So this part is well resolved. But the very early times are a little bit under-resolved.
What's the difference between the solid and the dotted line? Is there different thetas?
Different thetas, yeah. So the solid is on axis, theta equals 0. The dotted is right at the edge of the jet. Remember, it was 0.2, so a little bit inside of the jet. And then the dashed is pi over 4. So off axis, of course, nothing happens, but then as the jet expands, it starts to accelerate. And so at pi over 4, so let's say that the jet's like this. So if you're at pi over 4, sorry, it's hard to draw. If you're at pi over 4, you just as the thing expands, then you start to see the shock, and then you join the set-off solution at all angles, late times. Okay. Okay, so this is the problem, that it's a little bit it's under-resolved at early times, even as best we could do. Okay, but okay, so this is the kind of important thing, is that the energy spreads hydrodynamically. So models that calculate the light curves typically use a top hat. So what they assume is that you have constant energy and Lorentz factor as a function of angle out to some angle. And then at later times what happens is this top hat just expands. So at a later time you'd have a constant function like this, another top hat that was lower and broader. So it would go out to 0.3 or something. And that's effectively saying that the inner part of the flow immediately knows about that edge. And that's just not right. What happens hydrodynamically is that there's an expansion. So there's this thing right here that shows this is the energy per solid angle. It expands sideways, and then there's just a rarefaction that's communicating material inward, communicating the expansion inwards. So the middle part of the jet is still behaving as if nothing happened. So this is obvious hydrodynamics, but it makes a really big difference for the following reason. If you assume that this whole thing just got wider at a like this, so this is our new function, then all of a sudden you're sweeping up all of this mass, and so you slow down really quickly, and that's a runaway process, so you stop exponentially. So you just, as soon as this thing moves in, you just slow down really quickly. So is that clear? So then what really happens is the middle part is still moving quickly, and it's only the edge that is slowing down. And then at later times, finally here, the middle starts to know, so it starts to slow down. But this is quite late. And then eventually it becomes this, and then at very late times it becomes isotropic.
So models that ignore altogether the spreading can represent better the jet breaks. I mean that they just take into account no lateral spreading and when gamma is 1/3.
Yeah, so there's a bunch of effects, and let me show the light curve in a second. But yeah, the main effect of this, is that, the dynamics of the jet is affected, and it stays beamed for much longer than you'd expect. But yeah, this effect would, to some degree, smooth out the light curve. But it's a little bit complicated because it depends on your viewing angle and so on.
But I mean, it smooths out because of what? Because of the time scale? Because the light curve effect essentially, it just depends on the opening angle versus the actual beaming of the radiation.
Right.
I mean,
But
even if it doesn't expand sideways at all, if you just decelerate it, for a given opening angle, if you decelerate it, at some point the beaming of the radiation will be beaming cone of the radiation will be larger than the opening angle of the jet. So you see, you start seeing the sides.
Right.
That's the reason why it steepens.
of course, yeah.
So
That's right. But what this is showing is that there's a little bit of hot gas at radii bigger. So it's not, actually we do get a very steep jet break, which I'll show. And the reason is that the jet is limb brightened because, like I said before, the edges of the jet we're seeing at earlier times when the energy was higher. So as soon as the thing slows down enough that you stop seeing the edge, there's a very steep drop off.
right, that's the
Because it's like the donut on the edge, and all of a sudden there's no flux coming from larger angles. This effect counteracts for that a little bit, because you can see there is a little bit of energy at larger angles, so that kind of diminishes that effect to some degree. But you can see it's not a huge amount of energy, it's that, it's a little bit of energy.
The effect you mentioned is sensitive. It goes like gamma squared, right? So that's the main.
Yeah,
I mean, the flux drops by gamma squared roughly when you start seeing the edges.
right, I'm going to show you that in a second. Yeah.
That goes back again to the question of chosen of initial conditions. I mean, what's the time scale of the wave function wave to go across the...
The time scale is the sound speed in the local frame, and you have to divide by gamma, because in the lab frame it takes longer because of time dilation. So we can actually get this, we can describe this in a very simple way, as just the sound speed locally, and then if you account for the Lorentz factor of the bulk motion. But okay, so don't worry too much about the initial conditions, because at least because the spirit of this thing is to take the standard model and just explore it in multidimensional dynamics of it. And I agree that it's important to look at what actually happens, but what we're doing is we're just taking this Blanford-McKee angular patch and evolving it. I think it's a reasonable thing to do. Okay, but anyway, so this is kind of important, or it's one of the main results, is that this spreading is a slow process, and it takes much longer for the explosion to isotropize, and it stays jetted longer than you'd expect. And then this shows what you'd see. This dotted line is with the analytic expression, so it's kind of it just spreads laterally very quickly. This shows this function of time where 99%, 95%, 90%, and 50% of the energy is, the angle to which it goes. So in these analytic estimates, at some time, the energy just immediately spreads to the whole sky. Whereas in the simulation, we see it's a much slower process. So this is the difference. The spreading is much slower. Okay? And so what we see is that when we're looking at the light surface, so this is what we'd see, an observer sees, that it's the shape of it is much more asymmetric than you'd expect. So I should actually, and then this just shows a function of the set-off Taylor volume. That it just shows how beamed it is. It takes a while for it to become set-off Taylor, which it would do if it converged to 1. Okay, and then so anyway, here, so from that we calculate the radiation, and this, okay, there's a couple of things. In this case, we see sharp jet breaks, and it's because of this effect that the jet is limb brightened, and then as soon as you start seeing the edge, the flux just drops off. Okay, so that's point number one. Point number two is that you can see at very early times this rollover is due to this resolution effect, that our Lorentz factor is a little bit too low and our energy is a little bit too low. So really, if we just replace this with the Blandford-McKee solution, so very early probably isn't great, but this part on is good, and this is the what you'd see on axis as a function of time between radio and X-ray, and these are some analytic results that match pretty well at some time.
So
Yeah.
what you are showing now, what solid angle is observed?
You're on axis.
Exactly on axis?
Exactly on
This
axis.
have to be open somehow.
Sorry.
What's the opening angle anyway? You are observing conditions. I mean, you are observing not this delta function. Delta function will give you zero.
Oh, I see. So it's if the jet were coming at you,
Yeah.
that's what's happening. This is the symmetry axis of the simulation, and so there's some jet with opening angle 0.2, which is opening up, and you're right at the center.
So your
so
always
you're-
remains at the center.
You're the observer. Yeah, exactly. You're on axis. Okay. So and that's of course not all observers are on axis. So this is just an on-axis light curve. In fact, very few observers are exactly on
What's
axis.
the difference between different curves?
Oh, different. So this is multi-band. So this is radio. This is 10 to the 9 hertz. So up to the X-ray. And so right. And so these can be used. Sorry.
You have to assume something about the spectrum to.
Yeah. So I think so. What we did, starting a little bit over, is we just used the standard Mazaros and Rees and Perron and Sorry.
To the minus two something.
Yeah, all of those power laws, and all we did is we replaced the energy density with the computed energy density in a two-dimensional simulation instead of using this top hat model. So that's all we've changed. Everything else is standard on purpose.
And you
Okay.
assume energies from the entire region of the jet? Like from all inside the jet?
Yeah, everything's added up. But right, so of course at a fixed observer time you only see, you see
just
different
some
pieces of the
concept.
jet at different times in the lab
So
frame.
you just took some constant fraction of the energy density and said this is magnetic field, etc., and then
Yes, all the standard rings. But the difference is that the dynamics is two-dimensional. And then another interesting thing that we see is at late times we start to see the jet going in the opposite direction because it slowed down enough that its emission is no longer beamed away from us. And so we see these counterjets. And that's prediction that people, and some people have interpreted the data to mean that the thing was either you were seeing a host galaxy or that you were seeing the transition to the set-off phase. But it could be that you're seeing a counterjet. And there's one example where we think they may in fact have been observed. Okay, and then I'll just show you as is the last thing I'll show is that we can also calculate off-axis. So if you're not, so let's say the burst is going this direction and you're 0.1, 0.2, 0.3, whatever, away from it, then initially you see nothing, and then the light curve comes up at later times. So this is what you'd see if you were off-axis. And these solid lines here are if you were at the equator. So if a burst was going off in some direction, it would take some time before you saw it. It'd be very faint at first, but then you'd start to see the afterglow. In this case, you wouldn't have seen the GRD. And the other thing to notice is if you're a little bit off-axis, even though we computed sharp jet breaks for the on-axis observers, for off-axis a little bit, those jet breaks are shallower. So if you're, and most
you
of,
cannot see maybe those breaks in the light curve probably will not see.
they're much harder to see because it's much smoother if you're off-axis because you're seeing, yeah. So this is something we're working on right now is computing these off-axis. And then the other thing we're doing is computing in a wind medium. So this is a 1 over r squared. Everything I've shown you so far was in a constant density of 1 proton per cc. Now we're doing A star of 1, which is just this typical wind frugal for A star. And we get different dynamics. So we're also going to compute light curves from that. And then these light curves can be used to compare with observations at all frequencies from radio to X-ray. Okay. So I have more to say, but I think I'm going to stop because it's an hour. It's more than an hour.